Hello again, students of mathematical studies. Last time we was together, we was talking about E. I hope you having fun, because what was happening there was I was doing some E teaching and you was doing some E learning, right? See what I did there? Pretty good, huh? Yeah, okay, anyways. So, last time we talked about a bunch of mathematicians. We talked about Euler quite a bit. Right now we're going to talk about Gauss. Then we're going to talk again about Leibniz, who came up last time around, right? So, anyways, Gauss. You probably knows the Gauss problem. We talked about it a couple weeks ago. It's about this kid when he was 8 years old. His math teacher was like, "You kids are bothering me. You guys, everyone do add up all the numbers from 1 to 100." And all the kids is working hard, and they're doing this. They're doing like, okay, 1 plus 2, that equals 3. That's easy. 1 plus 2 plus 3, that's 6. Okay, now I add the 4, that's 10. Let's look at these answers as we're going along. 1, 3, 6, 10, 15. You see these things in Pascal's triangle. Them's the triangular numbers. We done talked about those, right? Well, so anyways, the question, what is the sum of all the numbers from 1 to 100? That question could also be this question. What is the 100th triangular number? Well, the way Gauss did his problem was he looked at it and he said, I'm not going to add 1 and 2 and 3 and 4. I'm going to do it more like efficient like. So you think about you get your 1 and you get your 100, right? So you get 1, 2, 3, 4, ... 97, 98, 99, 100. What he said is, at 1 and 100, that's 101. At 2 and 99, that's 101. At 3 and 98, that's 101, etc., etc. So what you got here are 50 pairs of numbers that sum to 101. So that's going to be 5,050. So Gauss answered this question in like a minute or two, and his teacher's like, dude, you're so smart, So anyways, that's sort of the Gauss story. Now, there's a notation for that I'm going to put up here right now, and it looks like that. And when you look at this thing here, it's got this symbol right here, right up here, that some people think is an E. But it's a Greek letter. It ain't an E. The Greek E is called epsilon. This one's called sigma. And what sigma means, it's an S. Like sum, when you're adding stuff. It says add it all together. Number on the bottom is what you start with. Number at the top is what you end with. All right? So here's the thing. The number at the top doesn't have to be an actual like ending point. You can go on forever and ever and ever and do an infinite sum. Now some people will think if you're doing an infinite sum, then the answer is going to be infinity, right? Like for example, if you did this, you said, look, I all know all the numbers, right? But here's what I want to do. I want to flip them all upside down and add them together. So let's suppose I want to add 1/2, or say 1, because if you flip 1 upside down, you get 1, right? 1/2 and 1/3 and 1/4 and 1/5 and 1/6 and 1/7. Now see, numbers are getting smaller and smaller because 1/7 is smaller than 1/6, and 1/8 is getting smaller. You get all the way down to 1 millionth. That's really small, right? So you might think because these numbers are getting down and being so super duper tiny, at some point this thing reaches some kind of a limit, But this particular question, that actually goes to infinity. That one ain't got no limit, or the limit's infinity, That's a way to say it. So you say the limit is infinity, but what does that even mean? It ain't got no limit, it just keeps going and going and going. I can show you a way to think about that in a moment. Maybe we'll come back to that in a little bit. But right now I want to talk about when Leibniz went to Paris. See, Leibniz was German. He worked for the German king, and the German king said, you got to go to Paris, do some business. He gets to Paris, sees these guys having great fun doing awesome math, And he's like, hey, kids, I want to play too, And they're like, go away, you're not smart enough. He's like, no, I'm plenty smart, see? So they gave him this problem. They said, you see if you can solve this problem, then we'll teach you what we're doing, right? So they gave him this problem. They said, what is the sum of the reciprocals of the triangular numbers? Now, if you think about it, just adding infinitely many things, then you might think it's infinity. But the sum of the reciprocals of triangular numbers is kind of an interesting question, Because you're talking about what is 1 plus 1/3 plus 1/6 plus 1/10 plus 1/15 plus 1/21, etc. So I'm going to suggest you do this. Put those things into a bit mapper, calculator type thing. See what you get for that one. Last time you was finding E, okay? Now I'm going to show you something about E real quick, okay? But in a minute. About this question. Leibniz got it right, all right? And I'll show you next time how he got it right. But right now I just want to say, hey, what is that, all right? So on the E problem, you went looking for that, and you found that was 2.71828, didn't you? Yeah? Yeah, it's about something like that, right? But the E problem was one of these summation problems. I'm going to show you like this. So you see what you're
Gotta
seeing right there?
apologize, man. It ain't a
Okay.
summation problem.
So I
It's
got
a
another
limit
question for you.
problem, and
You
it
can
looks
take a look
like
at this thing, but I
this.
think you can probably
Sorry
look at it
about
and be like,
that.
okay, I understand what's going on here, you know, because that's what this actually was. It was the sum of those things, all right? Now here's another question. Another question is, what if you take all the natural numbers, and instead of just taking their reciprocals, you take their factorials, and take the reciprocals. So 1 factorial is just 1, so that reciprocal is 1. 2 factorial, that's just 2, that's pretty easy too. But 3 factorial, that's 6, so now you got 1 6. What's 4 factorial? It's 24. So you take that reciprocal, it's 1/24, right? Wait a minute, what are we doing here? We're doing auto factorial? Yeah, that's right. So 5 factorial is 120, but 120 is 5 factorial, so 1/120th, what that is. And then 6 factorial is 720, and at 1 720 it's pretty dang small. So, you know, when you go to the next numbers, you're kind of done. So go ahead and put that stuff in your bitmap and find out what that is. What is the sum of the reciprocals of the factorials? I think you're in for a little bit of a treat on that one. All right? Okay, so let's talk about the question, because those problems, what's the sum of the reciprocals of triangular numbers? It's got an answer. What's the sum of the reciprocals of the factorials? It's got an answer too. Let's do one more that's got an answer, all right? It's the sum of the reciprocals of the powers of 2. Now what that means is, what's 1/8 plus 1/4 plus 1/8 plus 1/16 plus 1/32? I'm going to show you that one this way by imagining that you got this distance right here, and that's 1, okay? All right, 1/2 then's right here. So you get 1/2, 1/4, and then 1/8, 1/16, 1/32. See what's happening? You keep cutting down this little thing right here, but you keep going forever and ever and ever and ever and ever. You get there. That's the limit. And that limit, the sum of the reciprocals of powers of 2, that equals 1. That's kind of a cool problem. If you want to do something else, you could do the sum of the reciprocals of powers of 3. Figure out what that equals. It's kind of an interesting question too, but you know, we could deal with that one later. The one I want to deal with right now before I let you go is to answer the question about the sum of the reciprocals of natural numbers. What's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, etc., etc., etc. Because you keep adding smaller and smaller things, you might think this thing goes on forever, you know? Or sorry, you might think this thing has a limit. Oops, got the other thing around. Because, you know, those other ones are getting smaller and smaller and smaller. See, those is called convergent series because they go to an actual answer. They're also divergent series, which go to infinity.
Well, that was weird. What just happened? Anyway, we was talking about divergent series, which go to infinity. So here's the thing about adding up the reciprocals of the natural numbers. The reciprocal of 1 is 1. The reciprocal of 2 is 1/8. The reciprocal of 3 is 1/3. Reciprocal of 4 is 1/4. Reciprocal of 5, etc. We're going to know all the way up to 1/8 on this one. Just set this one up. Okay, so the reciprocal of 1/8 is, or of 8 is 1/8, you know, but you get the idea, right? You've got 1/8, 1/7, 1/6, 1/5, 1/4, 1/3, 1/2, and 1. We're adding all them together and going on and on and on and on and on. So here's the thing about how you can analyze this problem. It's kind of neat. Is I don't know where this is going, but I can look at something smaller. See? So 1 is 1. That's cool. We'll do that. 1/2 is 1/2, right? 1/3 and 1/4. Let's deal with this 1/3 by putting in something that's smaller than 1/3, which is 1/4. All right? Then what we're going to do, we got 1/2, 1/4 and 1/4. Then we're going to go 1/8, 1/8, 1/8, and 1/8. See, when we get to that last 1/8, we're at 1/8. The one in front of it is standing in for 1/7. And the one in front of that is standing in for 1/6. And the one in front of that is standing in for 1/5. See? And we just keep going like that. You notice what's happening here is if we're going to do the 16ths, we're going to have 8 of them. And if we're going to do the 32nds, we're going to have 16 of them. And if we're going to do 1/64th, we're going to have 32 of them. See what's happening here? So what we're doing is a sum of a bunch of things, you know. And what's this about? The point is 1 plus 1/8 plus 2/4 plus 2/4 is 1/2. Plus 4 of the 1/8, what's that? That's 1/2. Plus 8 of the 1/16, that's 1/2. And what we're doing is adding 1 and then a whole bunch of halves forever and ever and ever and ever. And you keep adding a half over and over and over again. The same thing you get. You keep adding 1 over and over and over 1. See, that one is a divergent series. That one goes to infinity. And therefore, the one that is the sum of the reciprocals of the natural numbers, which is a bigger number, has to be bigger. So this one's going to infinity. That one's going to infinity too. And that's the way to prove that the sum of the reciprocals of the natural numbers is a divergent series. But anyway, you don't even got to do that work. What you got to do is you got to ask that question about the one that was given to Leibniz. What's the sum of the reciprocals of triangular numbers? You're also asking what's the sum of the reciprocals of the factorials. And I think that's all you're doing right now, right? So that's pretty much it. Okay? So have some fun. We'll come back. We'll talk about some other stuff. By the way, about Gauss, in case you were curious about him, he's the guy that found a normal curve and all that stuff from probability and all that. The thing about a normal curve, it's actually an exponential relationship. The base of that thing happens to be, guess what? E. So if Euler hadn't found that, named that number, I don't know what Gauss would have been doing, you know. But Gauss did a lot of his work in the 1800s, in case you was curious, you know. So anyway, you know some stuff now about some of these guys, you know, like Leibniz and Euler and Gauss. Them's the big ones, you know. Oh, yeah, I think I already told you about Leibniz inventing calc, right? Because I don't know, something crazy just happened. Anyway, you guys have fun. I'll talk to you later. Bye.